All right, howdy folks. In this video, what we're going to do is discuss the mechanism of the reaction shown here. The content for this particular reaction, I would say, is a mix of electrophilic aromatic substitution chemistry, along with a little bit more advanced understanding of ketones and specifically alpha-beta unsaturated ketones that may undergo a conjugate addition. And so, like with most of our mechanism problems, the first thing I encourage you to do is to look at the starting materials and the products and see if you can determine which bonds are being made or broken. And clearly in the starting material, we have a double bond right here, and that double bond is not in the product. And so we're going to have to break that double bond. The other thing is we have this benzene ring in the product that's not here in the starting material. And so it's going to be this bond here, that carbon-carbon bond that's critical, that will end up needing to be made as part of this mechanism. Now, for those of you that are aficionados at electrophilic aromatic substitution, you may recognize the aluminum trichloride reagent is one that was critical for Friedel-Crafts alkylations and Friedel-Crafts acylations. The hiccup here is that we don't have an acid chloride or an alkyl halide. Instead, we have an alpha-beta unsaturated ketone. Okay, that being said, I'm going to encourage everybody to pause the video for a minute or so and actually work through this problem all on your own, and then come back and watch the solution, and that way hopefully you'll be able to maybe catch any errors you made, but also spend the time learning, which is one of the most important things. So please do take a moment right now to pause the video. All right, thanks for coming back. Let's see here. One thing about aluminum trichloride is it is a very good Lewis acid. And what do Lewis acids do? Of course, they look for Lewis bases. And one really powerful Lewis base is going to be this carbonyl oxygen. And that's actually going to mimic the Friedel-Crafts acylation, where that Lewis acid binds to the carbonyl oxygen first. So I'm going to draw the attack, and remember these arrows are the flow of electrons, and so we want to start with the lone pair on the carbonyl oxygen and draw our arrow from there. One common mistake I see is that students draw from the Lewis acid attacking the carbonyl, and that of course is backwards. All right, so this then gets us the Lewis acid complex. And let's add some formal charges. So this now looks like a protonated carbonyl, which would be plus, and to balance out that formal charge, we need a minus. And so formally, we'll put that on aluminum. Again, like with most Lewis acids, that negative charge is probably not actually localized on the aluminum. Most likely, it's a combination of all the chlorides that are surrounding it. But for the electron bookkeeping, we put the negative charge on aluminum. Okay, this now looks like a really great electrophile, and hopefully if you've been through the chapter on ketones, you can recognize that these kinds of protonated ketone intermediates are really great electrophiles, and they can undergo addition at one of two spots. So let me go ahead and just put in here that the nucleophile could attack there, and because it's an alpha-beta unsaturated ketone, we can imagine the nucleophile attacking at that distal site. And perhaps some resonance structures here would be really great to help us out to recognize that. So I'm just going to put my resonance arrow there, and then I'm going to pull up the carbonyl oxygen. Pull up the electrons in the carbonyl double bond towards the oxygen. We still need that negative charge on aluminum. And this by itself might be an okay intermediate, and certainly this is very similar to the kind of intermediate that acetal formation or ketal formation goes through. But we can draw an additional resonance structure on this alpha-beta unsaturated ketone by moving over that electron's one position further. And this now looks like a tertiary carbocation, and hopefully tertiary carbocations now are ringing some bells for the Friedel-Crafts reaction. And so it turns out that's exactly how the rest of this is going to go. So we're going to take our benzene here. And for those of you that have watched the other videos on the Professor Carbon channel, of which there are several electrophilic aromatic substitutions, I try to remind students that EAS always goes through two predominant steps, one of which is to make the strong electrophile, and then the second of which is to actually do the EAS mechanism. And here now we have our strong electrophile. And so this would represent E+. And now we can go ahead and proceed with the EAS mechanism. As a reminder, electrophilic aromatic substitution goes through two steps, the first of which is attack of the benzene pi system on whatever the electrophile happens to be, and the second of which is falling, having H+ fall off to regenerate aromaticity. I'm going to make sure I put that negative charge back there. Now we're going to just twist the benzene around a little bit, like so. For those of you that want additional practice at resonance, I'll remind you that this carbocation intermediate can actually be delocalized a couple of other places around the benzene ring. I'm going to refer to our other videos on electrophilic aromatic substitution if you actually want those drawn out. It's more of a reminder for folks that are looking for additional practice. Okay, now this H+ is going to kind of fall off. And for those of you that are experts now at arrow pushing mechanisms, you're smart enough to know that H+ typically just doesn't fall on its own. Almost always something is going to pull it off. And in this case, I think what we can do is invoke what now looks like an aluminum enolate. And so this can attack there, and then the oxygen can get its electrons back from that aluminum. And in the process now, we can kind of kick out an AlCl3 Lewis acid and then generate the full product protonated from the aluminum enolate-like intermediate. There we go. Oops. Forgot a couple of carbons there. All right, and so this would be the H then that we added over here. Cool, so that does it for this mechanism. Couple of steps, first of which is to coordinate the Lewis acid to our Lewis basic ketone, and then we're going to engage that ketone in a couple of resonance structures to get over here to make our strong electrophile for our electrophilic aromatic substitution, and then we're going to engage that in the two-step electrophilic aromatic substitution of attack, and then lose H+. And then in this particular case, we're going to kick off the aluminum trichloride that's there as a byproduct to make sure that we end up overall with the ketone. All right, if you've enjoyed this video, please do subscribe to the YouTube channel. That's how we know that these videos are actually reaching people, and it gives us some encouragement to continue making some additional videos. For those of you that want access to the PDF notes, whether they be blank or filled out after the video, you can access those on our Patreon page, and all you have to do is click the link up above in our channel to access that. Thank you again for watching these videos, and please share them with a friend.